Carlos Plain, a teacher from Durham School, shares that throughout his lifetime, he has focused on developing a precise and distinct hypothesis of the universe. He currently sees this speculation being scrutinized, something he welcomes, acknowledging that science progresses through such challenges. The James Webb Space Telescope is revolutionizing and testing some long-established ideas in cosmology, revealing an entirely new perspective on the universe. As we enter the new year, the telescope's ultra-deep field image has shown significant errors in our past understanding of the universe. Initially designed to reveal the first stars of the universe, this telescope is evolving into a challenger to past ideas and may bring about a completely new approach to cosmology. However, not all researchers fear these discoveries. Many experts in the field embrace these changes, as it had become increasingly evident that something was amiss with older theories. The consistency in calculating the universe's expansion rate cast doubt on earlier perceptions. Yet, for a long time, researchers clung to old assumptions. The cosmic microwave background, CMB, regarded as the oldest light in the universe, originated around 380,000 years post-Big Bang, when the universe cooled enough for protons and electrons to bond and create stable hydrogen atoms. This period, known as reionization, allowed the universe to become transparent to light. In 1964, American physicists Arno Penzias and Robert Wilson made a groundbreaking discovery using new radio antenna technology. They detected the CMB. This finding was long considered one of the strongest pieces of evidence for the Big Bang theory, earning Penzias and Wilson a Nobel Prize and securing their place in the history of astronomy. The CMB offered scientists an unprecedented look at the early universe, revealing small temperature fluctuations that provided insights into the conditions following the Big Bang. The CMB was also used to measure the universe's expansion rate and verify other cosmological assumptions. As early as the 1920s, cosmologist Edwin Hubble established that distant galaxies were moving away from us, with their speed correlating to their distance. This observation led to what is now called Hubble's law or the Hubble constant. While Hubble lacked advanced observational tools, his discovery, alongside the later findings of the CMB, prompted recalculations of the universe's expansion rate. These recalculations indicated a slower rate than Hubble's original estimate. Later cosmologists used type Ia supernovae, known as standard candles due to their consistent luminosity, as reliable measurement points for gauging cosmic distances. These recalculations, based on the CMB, suggested an expansion rate of approximately 67 km per second per megaparsec, while measurements from supernovae indicated a higher rate of around 74 km per second per megaparsec. The disparity in these calculations has been a contentious issue for scientists for decades, with many researchers acknowledging that something was fundamentally wrong with how the CMB and the universe's expansion rate were being interpreted. This discrepancy, known as the Hubble tension or SAA anomaly, suggests flaws in our fundamental understanding of the universe. These inconsistencies have profound implications, challenging our most basic beliefs about how the universe works. The issue has been known since the 1990s, when scientists began suspecting errors in the methods used to measure the CMB or assumptions about the universe's growth over time. The inconsistency between observed and predicted expansion rates became increasingly apparent. The Hubble tension suggests that our theories may require a drastic overhaul, indicating that key elements of our cosmological model could be deeply flawed. Now, with the advent of the James Webb Space Telescope, researchers are gaining unprecedented new data that may help resolve the issues with our understanding of the universe's expansion rate. These new findings are so significant that they could shake the very foundation of our previous cosmological theories. The telescope is revealing galaxies and systems so old and developed that they suggest the universe's formation may have begun well before the Big Bang. This challenges long-standing cosmological views, forcing scientists to reconsider the nature of the Big Bang and the expansion of the universe itself. Rather than merely discussing errors in data, scientists are now addressing what many describe as a crisis in current cosmological models. It's no longer just about mistakes. It's about rethinking our very conception of the universe. The new data from the James Webb Space Telescope reveals a universe far more astonishing than previously imagined. The Hubble tension, once a source of confusion for those adhering to traditional theories, is now a focal point for scientists, who must confront the possibility that our understanding of the universe may need to be entirely reimagined. As scientists continue to analyze these groundbreaking discoveries, they are also grappling with the larger question: do we truly understand the universe? To answer this, it's essential to grasp how science works. Cosmologists use complex mathematical models, careful analysis of data, and logical reasoning to make predictions and test hypotheses. Their conclusions rely on a combination of empirical evidence, established principles, and theoretical calculations. However, it's important to remember that science is a dynamic field, and theories are always subject to change as new data emerges. The term theory itself implies that scientific understanding is an ongoing process of refinement, not an absolute truth. One of the most critical sources of data for cosmologists is the light captured by telescopes, as well as the radiation and sound waves detected through radio telescopes. More recently, neutrino detectors and gravitational wave observatories have contributed to our understanding of the universe. The James Webb Space Telescope provides an invaluable tool for studying the earliest galaxies, their structure, mass, and the number of stars they contain. It can also trace the formation and evolution of galaxies over time. However, Webb is not without its limitations. For instance, it is sometimes difficult to distinguish distant galaxies from massive black holes that emit similar levels of brightness. This realization leads us to recognize that science may have accepted certain assumptions as facts while dismissing other possible explanations. The new discoveries from the James Webb Space Telescope highlight the importance of staying open to new ideas and theories. The data gathered by Webb presents a critical opportunity to replace outdated models with fresh perspectives, much like how science has historically evolved through groundbreaking discoveries. As scientists continue to unravel the universe's mysteries, they face the challenge of developing new explanations for what they are uncovering. These revelations are causing significant shifts in the fundamental concepts of our understanding of space, prompting a reassessment of our knowledge of cosmic evolution and the forces at work in the universe. Our current models of physics and astronomy are still largely rooted in the 17th century laws of Isaac Newton. While his laws of motion and gravity have served as the foundation of our understanding of physics on Earth, they were eventually found to need modification when applied to space. This led to Albert Einstein's groundbreaking work in the early 20th century, particularly his special theory of relativity in 1905, which revolutionized our view of spacetime and motion. Einstein's general theory of relativity, published in 1915, extended this revolutionary thinking, proposing a mathematical model that explains the gravitational effects of massive objects on the curvature of spacetime. While Einstein's theories were crucial in transforming our understanding of the universe, he himself acknowledged their limitations. He believed his theories would never fully account for all the complexities of the universe and dreamed of a unified theory that would integrate all of physics. Yet, no scientist has succeeded in achieving this comprehensive model of the universe. It remains an open question. What might this theory look like, and could it earn someone a Nobel Prize? Among the primary suspects for the current cosmological crisis are dark matter and dark energy. These concepts, which make up about 95% of the universe, remain largely theoretical, as neither has been directly observed. While these mysterious substances are central to current models of the universe, their exact nature is still unknown. Some experts speculate they may not exist as we understand them, requiring alternative explanations for the observed expansion of the universe and the dynamics of galaxies. Others suggest that dark matter and dark energy may have evolved over time, altering their properties in ways we don't yet understand. Another possible explanation involves gravity, a force we know causes attraction between masses. Yet even this force, as described by Einstein's theories of relativity, remains an area of ongoing study. Scientists are exploring the possibility that gravity could have properties we don't fully understand, or that an entirely unknown force might be responsible for the gravitational interactions we observe. As the field of cosmology continues to evolve, scientists are revisiting some of the constants long believed to govern the universe. Cosmology, after all, is an ever-developing field, driven by humanity's relentless pursuit of knowledge, from the early observations of the night sky by ancient civilizations to the advanced instruments we use today. Each step in this progression brings new challenges and opportunities for discovery. As our understanding deepens, it's becoming increasingly clear that we may be standing on the brink of a new era in cosmology. The James Webb Space Telescope, with its cutting-edge technology and remarkable capabilities, is at the forefront of this revolution. By providing unprecedented insights into the earliest galaxies, star formation, and cosmic evolution, it is helping scientists probe deeper into the universe's origins and the forces that shape it. But as exciting as these advancements are, they also underscore the complexity of the questions still to be answered. For all the progress made in understanding the cosmos, fundamental questions remain unresolved. What are the true natures of dark matter and dark energy? How does gravity truly work on cosmic scales? Can we develop a unified theory that accounts for all the forces of nature? These are not just theoretical questions. They are central to how we understand the universe, its past, its present, and its future. The discoveries of the James Webb Space Telescope may hold the key to unlocking these mysteries. But they also challenge us to think in new ways and to be open to the possibility that our models and assumptions may need to be rewritten entirely. As scientists continue to explore the cosmos, they must also confront the reality that our knowledge of the universe is still incomplete. This is not a failure. Rather, it is a testament to the ever-evolving nature of science. The more we learn, the more we realize how much we have yet to discover. In the end, the pursuit of knowledge about the universe is not just about answering questions, it is about asking better questions. And with every new discovery, we move one step closer to understanding the vast, mysterious, and awe-inspiring universe that we are a part of.